Welcome to this explainer. Today we're unpacking nature's ultimate continuous balancing act, chemical equilibrium. A lot of people think equilibrium is just this static stopping point where everything freezes and nothing happens. But actually, it's a highly dynamic, constant state of microscopic adjustment that's happening right behind the scenes of literally almost everything around us.
Okay, let's dive into this. What we're looking at today is a decoding of a beautifully concise set of handwritten notes from our source material, and they cover an enormous amount of ground, all the way from invisible gases to acids to solid precipitates. We are going to unpack all this dense chemistry and translate it into a really clear, logical story about exactly how molecules find their balance.
So, here's our roadmap for today. We're exploring three totally distinct arenas. First, gas phase equilibria constants. Second, acid-base buffers and titrations. And third, the solubility product and common ions.
Let's jump right into Arena 1, the air, looking at gas phase equilibria constants. When gases react inside a closed system, they have to follow some very specific mathematical rules. Now, usually when we're talking about your standard liquid solutions, we use molarities to measure concentration, right? Well, gas systems operate totally differently. The gas equilibrium constant, Kp, essentially throws molarities right out the window. Instead, it relies entirely on what we call the partial pressures of the individual components floating around in that closed space.
But what exactly is a partial pressure anyway? Well, computing it is actually quite straightforward. You just find it by multiplying the specific mole fraction of your target gas by the total pressure of the entire system. Think of it like calculating the exact individual share of the total pressure that one single specific gas is responsible for. It's just their slice of the pie.
So the crucial point is this. What actually changes these mathematical constants? Our source material makes this incredibly clear. The numerical magnitudes of both Kc and Kp are shifted exclusively by changes in temperature. That means you can pump in more gas, you can change the volume of the container, but the constant remains totally mathematically constant, unless you turn that heat up or down. Moving right along to Arena 2, the liquid. Here we're focusing on acid-base buffers and titrations. Let's descend from those invisible gases down into the liquid phase. Unlike strong acids that just shatter apart instantly in water, weak acids are a bit more stubborn. They exhibit a partial, incomplete dissociation. And the super delicate balance is regulated by the acid dissociation constant, known as Ka. The mathematical engine governing this split is an equation where Ka equals the concentration of H+ times A- divided by the concentration of the original Ha. Now, check out this beautiful mathematical symmetry that happens during a weak acid titration. Right at the exact half-neutralization point, the concentration of the undissociated acid, Ha, is perfectly equal to its conjugate base, A-. And because those two values are identical, they cancel each other out, and the complex math magically simplifies. Suddenly, Ka simply equals the concentration of H+ ions, which means your pH is exactly equal to your pKa. It is just this perfect fleeting moment of chemical balance. And this specific balancing act is actually what makes complex life possible, all through something called a buffer solution. Think of a buffer as a heavy-duty chemical shock absorber. It's designed specifically to minimize any drastic changes in pH when small amounts of acid or alkali are introduced. It completely protects the system's balance from outside disruptions. Here is how that shock absorber actually works in an acidic buffer. It's a totally brilliant dual-action mechanism, basically a chemical 1-2 punch. Step 1, the weak acid stands by, ready to neutralize any added OH- that tries to spike the pH upwards. Step 2, the conjugate base acts like a sponge to consume any extra H+ ions that might try to crash the pH downwards. So it actively works from both sides to keep that liquid perfectly, stably balanced. Okay, so gases balance their pressures, and liquids buffer their pH levels. But this brings up a really fascinating question. What happens when equilibrium hits a physical breaking point? Like what actually occurs when the system literally can't take any more input? Which brings us to Arena 3, the solid. Let's look at the solubility product and common ions. So here in our final arena, we're exploring what happens when a sparingly soluble ionic salt reaches its absolute maximum limit in a liquid. This limit is defined by the solubility product, or KSP for short. You can think of KSP as a strict mathematical ceiling. It's the absolute maximum amount of a solid that can physically dissolve into a saturated solution before the liquid essentially says, nope, no more.
And nature enforces this ceiling very strictly, leading to a major precipitate alert. If the calculated ionic product in your solution ever surpasses that KSP value, a physical consequence happens instantly. The solution becomes totally overloaded, the equilibrium breaks its invisible bounds, and solid matter literally falls straight out of the liquid as a precipitate.
Now, what's really interesting about this slide is a phenomenon called the common ion effect. If you try to dissolve a salt into a liquid that already contains one of the exact same ions that make up your salt, the absolute solubility drops sharply. It's practically like trying to squeeze your way into a crowded elevator that's already packed with people just like you. There just literally isn't any room left. The mechanics behind this elevator analogy are deeply tied to balance. Because there's already a high initial concentration of that shared ion present in the solution, it essentially shoves the dynamic equilibrium in reverse. It physically forces the position of equilibrium backward, preventing more of your solid from dissolving and ensuring that the universal balancing act is strictly maintained no matter what. Let's wrap this all up with our conclusion, the universal rules of shift. We've traveled from the invisible partial pressures of gases, straight through the buffering actions of liquids, all the way to the solid reality of precipitates. And this brilliantly illustrates what ties it all together: 3 distinct shift triggers. In gases, only temperature changes can shift the actual magnitudes of Kc and Kp. In solids, surpassing that KSP ceiling instantly forces the system to form physical precipitates. And in mixtures, high shared ion concentrations force the whole equilibrium backward. It is the exact same universal principle of balance, just responding to different triggers across different phases of matter. Every single chemical system, no matter what phase it's in, is constantly adjusting to maintain its balance. So the question I want to leave you with today is this: since balance dictates all of these microscopic reactions, how is dynamic equilibrium shaping the macroscopic, unseen world right in front of you every single day? Keep an eye out for nature's constant balancing acts out there. Thank you so much for joining me on this explainer. Keep learning, keep focusing, and I'll catch you next time.